Hello, welcome back to my new video about high-level synthesis and optimizations. In my previous video, I started discussing about high-level synthesis where we took an example of moving average function and we went about performing high-level synthesis where we took the C code, performed the synthesis to extract the generate the RTL, and finally implemented that on our FPGA board. So today, all that I'm going to talk about is optimizations. So optimization, high-level synthesis optimization is a process where we can control few dials or provide few inputs to the high-level synthesis tool to get our desired RTL. This tool performs certain optimization by default, but using something called as pragmas, we can dial that to our need or modify the synthesis options. So pragmas help in controlling how the RTL is generated or how the C code is interpreted in order to generate the RTL. So for today's example, we are going to take bubble sort as an example. So we'll write the bubble sort in C or BDL, then provide few pragmas and generate the RTL according to our need. So in this, we are going to target two elements of the pragmas, that is how an array is interpreted and generated the RTL for that, and how the for loops are being synthesized for our RTL. So those are the two main things that we are gonna look at today. So this is our main function that performs bubble sort. So this function initially reads the input in data and index respectively from the files that we provide, and also it keeps the out data.txt file or out data.clv while we are simulating to write the output once the sorting has been done. The data that is being read from index is being assigned to a variable index n, and based on that index n, that will control the for loop to read the array data or the input data. So based on the index value, the respective in data is being extracted from the file and saved to B array, that is our data array. And this is the core functionality of our bubble sort, where it will evaluate the current array element and the next array element to see which is smaller and swap accordingly. And then once the swapping is done, the same array is being written out to the file, either in C or in our synthesis. So here, as I talked about, we are going to target two pragmas and understand how pragmas work. So there are several other pragmas as well provided by Cyber Workbench, whether it mainly over here, as I mentioned already, arrays, how the for loops are being controlled, how loops in general are being controlled. For functions, we have something called as inline, goto, pipelining can be used for functions, for any loops. So these different pragmas have their own advantages and disadvantages. As they say, for each option there is always a trade-off that comes along with it. So here, to get our hands dirty with optimization, I'm just gonna concentrate on how array is how we can provide pragmas to control the array synthesis and for loop synthesis. Before I proceed forward, performing optimizations and seeing how the results turn out in the real world, I just want to gloss over the theoretical points regarding the different pragmas I'm going to use. So for array, either it's going to be register or a RAM. If it's a register, the elements are implemented as individual registers or individual flip-flops. So here the main advantages will be fast parallel access. All the array elements can be accessed simultaneously. Theoretically, zero cycle latency. When we are reading any of these data, we can do multiple concurrent read and write. But the disadvantages are high area consumption and high power consumptions as well. But this is mainly used when the array size is really small and for requirements where data access or data write speeds are higher. If we go for RAM, this will use dedicated block memory units to store the data. So the area consumptions will be less, but the latency will be high since the data path to go to the block memories and retrieve it and get it back to the functional units will be high. Here also the disadvantage will be parallelism. So since there are limited ports towards dedicated for the block memory, parallelism will be limited. But this will have an advantage giving low power and low area. So these are the two different optimizations that we can perform towards an array. Coming towards the loops, we have a concept called as unrolling, where basically the for loop is unrolled or opened up, and each sequence is uh, in the C. It'll be written one after the other instead of all combining inside a looping function. And once the HLS sees these statements one after the other, it'll just parallelize them and execute all the different all the statements of each iteration parallelly. So, however, if you don't unroll it, everything will be performed sequentially. So the advantages of unrolling will is uh, higher performance rate, basically low latency, uh, but the main drawbacks will be high area consumption, higher power, and poor scalability. So if the iterations are very high, then unrolling will have a negative impact. If we don't perform any unrolling, the advantages that we get is lower area, lower power, and scalability will also be really good. So these are the two different uh, pragma states that we can provide for individual element. So now let's go back to our code. Here we can provide the pragmas for the array. I've already provided as register, and for loops we'll just give it as cyber, unroll, and whatever our condition is. For unrolling we can either provide complete unrolling, no unrolling, or partial unrolling as well. So here we are just for the sake of understanding, we are just gonna go with two states: full unrolling or no unrolling. So for this understanding, I'm going with three designs. In design one, I'm giving array as a RAM, and for two loops, I'm giving complete unrolling. For design two and three, I'm assigning array as a register, but I'm toggling the inner for loop whether it's going to be fully unrolled or not unrolled. I've already implemented the different pragmas, synthesized the code, and extracted the results from these, uh, so, which can be seen in the synthesis history. So I have four different designs here. The first design was a baseline where I hadn't provided any pragmas, just relied on HLS to use its default synthesis options. But for second, design 2, 3, and 4, I provided my pragmas and uh, evaluated the result. So to save some time, I've already gone ahead and synthesized my BDL code with different pragmas for the individual designs. Here, the design one doesn't have any pragmas. I use this as the baseline. For design two, I provided the pragmas register and complete unroll on both the for loops for the bubble sort. For design 3, I assigned the array as a register, and I fully unrolled only the outer loop and uh, no unrolling for the inner loop. For the fourth design, I again provided the array as a register and provided fully unroll on both the for loops that were used for the register. So based on the pragmas, these are the characteristics of the design that was generated. We can also see the synthesis graph. This helps us evaluate area versus latency, how the characteristics of individual design lie. Here we can see only 2 points since Three of the designs were on one point with latency 6, and only one design had latency 9. So that's why you can see only 2 points over here. So yeah, that's the high-level synthesis optimization, where I use the arrays and loop pragmas to control the synthesis of my design. We can also use other pragmas based on our requirements, based on our functionality, to better control how the RTL is generated. Also, using Cyber Workbench synthesis window, we can evaluate how different designs are performing and their individual characteristics and how they vary over different designs. So yeah, that's high-level synthesis and optimization. Hope you learned something. Thank you and have a great day.